Hey 30-2s. Here is a video where we're going to learn how to solve equations using logarithms. Now, in general, we're going to use a logarithm to solve an equation when we aren't able to make the bases the same. So that's when I want you to think that's probably when I need to use a logarithm. Now, a couple things to remember. Our most important formulae, which are on our formula sheet, of course. And what I just want you again to remember is that multiplication turns into addition, that division turns into subtraction, and those two aren't going to be super duper important for us today, but they'll play a part. But it's this last one here, the power law, which we're going to use a lot, where this power can turn into a coefficient. Okay, so there's our main three laws. Let's go and solve some of these. So like I said, the power law is going to be probably one of the big features of today. Let's go and solve these things. So solve algebraically, which means show me some work, right? First thing I want to try, can I make the bases the same? Well, if you look at A, B, and C, I can't. So this is where I'm going to need to use a logarithm. So how a logarithm is going to help us solve this is I'm going to do what my teacher told me when I was a little guy. What I do to one side, I do to the other. And again, the reason why is that maintains equality. It's a balance. We haven't changed what this thing is equal to, just how it looks. Okay, well, we're trying to isolate for y. So what we're going to do here is we're going to use that power law. So that power of y becomes that coefficient. And now, okay, look, now I can easily isolate for y by dividing both sides by log base 10. And there it is. There is what this is equal to. Now I can put this in my calculator and round to a decimal, but I don't want to. This is the exact value of that equation. Okay, let's try another one. Let's go to hot pink. So the next one, B, I say to myself, can I make the bases the same? No. So then I'm going to use a logarithm. So I take the log of both sides, just like that. Again, that power becomes a coefficient. So that's why that power law is so important. Just like that. And again, now I'm going to divide both sides by log 5. And again, there it is as an exact value. And remember, friends, when we don't write a base of a logarithm, that it is really base 10. It's a common log. It's just worth noting that when I do take the log of both sides, I could make the base anything I want, but it makes most sense to make it base 10. Okay, last one, same thing. Can't make bases the same. Take the log of both sides, right? What I do to one side, I do to the other because it maintains that equality. Power becomes the coefficient. And divide both sides by log 6. And there we go. Okay, easy peasy. So again, the logarithm, this function, is really helping us solve for these unknown exponents and in a pretty quick way. Now, a few slightly more difficult examples. Okay, what have I added? Well, if I look at D, I've added in a coefficient of 3. So what I'm going to do is I'm going to divide both sides by 3 first. Right? Remember, we're trying to solve for x, the exponent. Let's get everything away from it that we can. So the inverse of the multiplication of 3 is divide by 3. Now I take the log of both sides, just like that, log 8 over 3. Again, our power becomes our coefficient. And now something important here, when I bring this down, I'm going to put that x plus 1 in parentheses like that. Because I just want to make sure that when I'm solving here, that I know that this has to be in parentheses because it's being multiplied to the log 4. Okay, now I'm going to divide both sides by log 4. And I'm going to write that correctly and do what I said I was going to do. Divide both sides by log 4. just like that. And I can finish this thing off by subtracting 1, and I didn't leave myself enough room, so I'm just going to subtract 1 there, and there it is. Okay, there's the solution to that one. E is going to be essentially the same thing. Okay, again, what I'm seeing here is I'm seeing this coefficient. I need to get rid of that coefficient by dividing. What I don't want you to do in bright red, what I don't want you to do is to multiply the 2 and the 3. The reason why I don't want you to do that is that's bad math. Can't do that. No can do. One's a base, one's a coefficient. So again, I'm saying to myself, I want to isolate for x. So let's divide by 2 because it gets everything away from x, or starting to get stuff away from x. I can't make the bases the same. Let's take the log of both sides, right, to maintain that equality. Power becomes the coefficient, just like that, equals log 6. Okay, here I'm going to multiply both sides by 4 and divide by log 3 in the same step. So it'll be 4 log base 10 of 6 over log base 3. There it is. Okay, I'm going to leave F. It's the exact same thing. Divide both sides by 10. All right, so again, I'm using logs when I can't make bases the same. Logs are our friend in this case. Now, there is one more thing that we can do, and this last thing we can do is actually going to help us develop a bit of a shortcut, which I'll explain in a minute. We're going to use the last formula that's on our formula sheet, known as change of base. So how change of base works is when we're dividing two logs here, right here, we can simplify them into a single log. And if you notice how this works, is the argument of the numerator becomes the argument of the simplified log, and the argument of the denominator becomes the base of the simplified log. Okay, so let's go back and rewrite some of our answers from above. Let's look at these three here in particular. I'm going to switch pen color to purple. So I'm going to use change of base on this first one here in blue. So change of base tells me this. I can simplify this into a single log. The argument of my numerator becomes the argument of my simplified log, and the argument of my denominator becomes the base of my simplified log. These two answers are the same. They don't look it, but they really are. Let's do a couple more just to make sure you have this, because this is an important skill. So again, if I want to simplify what's here, my argument of my numerator, the 8.32, becomes the argument of my simplified log, and the argument of that log there becomes the base, just like that. Okay, so I'm hoping what you're seeing is, hey, simplifying this isn't really too bad. Why would I want to do such a thing when both of these, he's telling me, these are all the same, right? So really, I'm happy if you write it either way, but you can see why we would maybe prefer to write it in the purple, because it is simplified. Here's the other reason, friends. There's a shortcut, which we just almost made, or maybe we can see right now. I want you to look at the original question, and I want you to look at our new simplified answer here. I want you to see if you can notice something. In the original question on A, the base of the exponential was 10, and the base of our simplified logarithm is 10. Let's go to B. The base of our exponential here was 5. The base of our new logarithm is 5. C. The base is 6. The base is 6. All right, so interesting. The base of the exponential is the same as the base of the logarithm. Now, here's what I want you to notice. The 81 and the y essentially switch places. Do you see that? The y is over here where the 81 was, and the 81 is now with the 10. look at B. The y and the 8.32 switch. The reason why these are switching is because an exponential and a log are inverses. When we say inverse, it means we can undo something. It means we're switching x and y. So what we've just developed, friends, is a shortcut. What we can do now is we can go right to these answers like this. I would prefer, in a perfect world, if we did it sort of this long way by taking the log of both sides, but I'm going to guess that most of you are going to prefer the shortcut. So here we go. There's a quicker way to convert between forms. Here's how it goes. My little expression is this. Base stays the same. So we're going to convert this exponential here. So log base b, maybe I'm going to use the rainbow because I can. Log base b, so the bases stay the same. And the other two parts switch. So the x is going to go where the y was, and the y is going to go where the x was, just like that. So again, that's my little expression. Base stays the same. The other two parts switch. The other two parts switch because they're inverses. This is on your formula sheet. So here we go. Let's see just how quick we can do these ones. Again, these were the ones from above, but let's just practice with them. So what I say to myself is the base stays the same. So log base 10, the other two parts switch. So the y goes where the 81 was. The 81 is our argument. Well, that's a heck of a lot quicker than what I did before, isn't it? Try B. Base stays the same. So log base 5 and the y and the 8.32 switch. And on the last one, log base 6 of 12 is equal to x. All right. I mean, that's pretty simple. Why I said I would prefer you did it the other way, though, my friends, is because we all don't, depending on our calculator, have the ability to put this into our calculator. So some of us have to use change of base anyway. All of us with TI-83s have to put that in their calculator anyway. So as much as this little, I'm calling it a shortcut to get to this answer, the simplified answer right off the bat, some of us still may have to use change of base. So there it is, my friends. That's how you use a logarithm to solve for an unknown exponent.